something, and then you go to your orders and see, okay, order is successful, and I can see my orders in the order list. Have you ever faced a scenario where you ordered something, but now you went to your orders list, but you don't see anything? I don't think anyone has faced that, right? So that means this is consistent. So Amazon is a huge, like their backend systems are huge. They do a lot of stuff when you order. So but still, your data is consistent. If you order something, and if it is successful, you will always see that in your orders list. It will never miss out. So that's consistency. Another concept is partitioning. So in many cases, basically, your data will keep grow and grow. Now there is a limit there also, right? If your table has a lot of data in GBs of data, TBs of data, how will you if you fire a query, it will take lots and lots of time to just give you just return a simple response. Select star, even if with primary keys and all the indexes, everything, uh, it will take minutes to just give you a simple response. Forget about join and all. So now here comes DB partitioning. Again, horizontal and vertical. In DB partitioning, horizontal, basically you have a table. If you're talking about vertical partitioning, you cut it. So based on your use cases, let's say you have a use case where you need just a column A, B, C. So you cut, and your entire table had 6 columns A, B, C, X, Y, Z. Now what you do, you cut it in 2 tables. One has ABC, one has XYZ. You store these tables in on different nodes. Now you ultimately you have reduced load on your node. You have reduced the amount of data that table stores. Same way, but again, this there are a lot of drawbacks in this, right? What if you want C and X? You have to query, and you cannot do join. It is distributed, so a lot of things are there. When you come to horizontal partitioning, so horizontal is always good, right? Horizontal scaling, horizontal partitioning. So when you come to horizontal partitioning, slice your table like horizontally. Now how do you do that? Let's say you have a order table, and order, let's say let's take a very simple example. You have users table, where you store simple user IDs or user names. That's it. Now you have millions of users like Facebook. How do you divide that? Maybe you can, a naive strategy would be, okay, users whose name start with A, I'll keep it on node 1 or instance 1, machine 1. The users whose name start with B, I'll keep it on machine 2, and so on. Now you know that if you want to query any user whose name start with A, you are sure that all the data for that user resides on node 1 or machine 1. Same way, you know, for every user whose name start with a certain alphabet, that which machine you need to talk to. So that's horizontal scaling. Okay. DB replication. Now again, just similar to what we've discussed about servers, your DB is again a machine, right? It can fail as well. It can crash. And if a DB crashes, and if you don't have a backup, I mean, you can't even imagine that. So DB replication is very important. Whatever you do, horizontal partitioning or vertical partitioning, you have to have replicas of that data somewhere, right? You have to keep multiple replicas. So usually that's done by DB replication. Yeah. Okay. So any questions so far? Okay.
Please, guys, do ask if you
Actually, I
have
have.
questions.
Actually, I have. When we are talking about the instances, the what are the instances here? Actually, the instances that on we are talking about the server or the instances of the actually we are talking about the collections.
No, so instances, I mean, it is same as a machine, it is same as a server. So I'm using these words. So they mean same thing. You have a machine where your server is running. So one machine, one server, one instance. Is it clear? Okay. I'll take it. I'll take that as a yes. Okay. Okay, so these were the concepts, but it may be like maybe some of you know about these, maybe some of you don't. So that's like a theoretical information, right? We will do a real life problem, and then we will see how we are using these concepts to build an application, a backend application. Uh, yeah, so that will come a little later. These are the system design components, right? When you're designing a backend application at high level, before you start to code, you have to know what will be my services, how will you store a data, how you store data, what kind of data it will be, whether it will be relational data or unstructured data, uh, will there be asynchronous jobs. So a lot of things has to be thought through before you actually go into coding. So and for that there are some components that we will use when we are designing an such kind of backend application. Okay, so I'll start with first is API gateway. So API gateway is basically a door to your application. So imagine that um, a request is coming to you. In monolithic cases or in older era, what how it used to do, it used to come is a client directly calls a server, and that's it, and you serve that request. Sorry. And now that is not the case, right? If you have microservices, there will be n number of microservices, right? We just talk about food ordering app there, where you have a ordering service, and then you have a registration service. But for the outside world, it is a single app, right? The backend application, backend system is the same. So now when request comes, how do you how do you know that which server it should go? Because your all the services will be in your cloud, yeah, right, in your cluster. So how would you decide where the request should go? Here comes the API gateway. API, so one of the job of API gateway typically is basically route your request to appropriate microservice based on the request. So if your request is for ordering, it should go to ordering microservice. If your request is for basically maybe restaurant registration, it should go to that service. If request is just for payment, it should go to payment service. There can be a number of services. Other things the API gateway can handle, depending on the application you are building, is basically authentication. It can check whether a request that is coming to you, it's a valid request from a authenticated user or not. So as a user is authenticated when you have already provided a login and password, and then after that everything you do is authenticated because you have a valid password. So it can check whether request is coming to you is authenticated or not. If not, it can block then and there itself. No need to even reach your microservice, right? Why the microservice needs to bother about the authentication part? So API gateway can handle that as well. So and appropriately route the request to login service. Maybe we can have a separate service, login service or user service. So that's the job of API gateway. Next is load balancer. As we discussed, right, we can have multiple instances, multiple servers of each microservice. So now how would you distribute? API gateways, it's not API gateway's job to distribute the load, right? So that's the job of a load balancer. API gateway will send the request to appropriate load balancer, and then load balancer has the job. Okay, it will see, okay, microservice one that I'm dealing with that is connected to me has a lot of load. Okay, let's not send the request to that. So it will send the request to the next microservice. Depending on the algorithm you are using in load balancer, it will do that. A naive or a very easy algorithm can be round robin. First request, first microservice, second request, second microservice, and so on. So again, load balancers can be of different types. They can be physical load balancers, software load balancers. Like you can dig in deep in the load balancer, but at high level you have to have a load balancer in front of your microservice. Next is database. When you're designing a system, you need to know what kind of data you are going to store, how you are going to use that data. In an ordering app, though you will have a lot of data, and there is like in the market, there is a misconception that SQL is slower and NoSQL NoSQL databases are much faster. This is not the case. Many big firms, they are using SQL databases, and it's almost as equivalent to as NoSQL. Just that NoSQL has specific capabilities where they beat SQL databases. So now in an food ordering app, when you are storing an order, that's a transaction, right? When you need asset properties, you need consistency, then you have to you have to use SQL databases. You cannot use NoSQL. There is no transaction, there is no rolling back, nothing like that. So based on the use case, you have to decide what kind of database you are going to use. When you want to just store maybe user behavior or some kind of unstructured or raw data, you will go with NoSQL databases. Caching. Caching, people use caching just like that. I mean, okay, when someone asks you, okay, make your application performant, let's do what? Let's do caching. But caching is not as easy as that. You have to think it through, because caching stores everything in RAM. It doesn't store in hard disk, right? So when you are storing everything in RAM is costly. It will cost you a lot. You need to know that what and how much data you are going to cache, for how long you are going to cache. So you need to do a proper homework before you start just directly caching. So that's another concept that needs to be thought through before you actually introduce it. Then comes message brokers, or some in simpler terms, queues. Message broker, whenever you want to do something asynchronously, right? When you want to when you want to process something in the background, you can use a queue. What's a queue? It's a simple data structure, right? And at the same time, in the market, it is a software. So what it does is, you send a message to the queue. There are listeners to the queue. They keep listening, and they will receive that message and process that message. Now this makes your entire flow asynchronous. So as soon as you send a message to the queue, you get your response immediately back, and that's it. You forget about what happens to that message afterwards. So and from there, it runs in a separate thread. It runs separately, and it's an asynchronous process. So that's a queue. Yeah. So any doubts so far?
No, sir.
Okay, cool. So next is actually, I had I thought I'll discuss a real life example, and we'll design an application here. So I have this easy diagram here. So let's say we are trying to build a, here we will design, like we will use the concepts that we just discussed. We'll use the components that we just discussed, and we'll try to resolve the problems that we usually face when we are building a backend application, a scalable backend application. So typically, let's talk about food ordering app, right? How the interaction is, yeah, there is a client which sends a request. Okay, I am ordering something. There is a server which handles the request. Okay, your order is done. Stores the data in database. Maybe sends notification through different channels, messages, third-party services, and we're not bothered about that. It sends a notification. That's it. Now the problem. Uh, Now we have to look for what are our bottlenecks, single point of failures. As we can see, server, if server crashes, and the client is left he cannot do anything, right? If the DB crashes, server cannot do anything. So now what we need to do is, we have to scale. How we can scale? Let's say, since we know server is a bottleneck for us, let's add more multiple nodes of server. Okay, so now we have 3 server nodes. Now we know that, okay, if one fails, we have other 2. But now, as I told you earlier, how will the request come to this each node? You need a load balancer. So here comes a load balancer. So the client sends the request to load balancer, and the load balancer will distribute the request. Now, as we discussed, this is one microservice, right? This is order. Let's say ordering app, order service. Now, what's next? Uh, this is order service. Now there is a, as I said, there could be a payment service, right? When the client is going to make a payment. Now, how would this request go to payment service? We discussed a component there. There is API gateway. So let's introduce an API gateway here. Okay. Okay. So now here is an API gateway. I hope this is visible. Is this too small?
No, that's fine.
Okay, cool.
Not too small, that's fine.
Okay. So now we know that a request comes to API gateway. API gateway knows where to send direct the request. It sends the request to load balancer, and then depending on which service it needs to send. So for, let's say we are talking about order service, so it sends a request to order service, and then order service interact with DB. Now, what is the next bottleneck? This DB. This is a single DB, right? What we can do is we can again do a similar thing that we did with order service. We can have multiple instances of DB. If one fails, other is there. So now again in the DB, which DB, how the DB will store this data, all the DBs, right? There is a so you need to have a sync mechanism or some kind of mechanism which says, okay, I need to store this data in all the DBs. So you can probably have a wrapper here. So this is my DB. Now this is my wrapper. Now this is another is, it could be an application, it could be similar to load balancer. Now what is does is basically it handles how the DBs store data. So maybe a wrapper DB. Now next is you make a question that we have a load balancer, right? This could be my single point of failure. A single load balancer, uh, it cannot, maybe when we have burst of requests, millions of requests coming in, it cannot handle. Same way with API gateway, but they have very limited functionalities, right? Order service, when you're ordering, it is doing a lot of stuff. It is interacting with DB, it is sending notifications, it may be fetching data from different services, maybe a user service. It is doing a lot of stuff. So that could be a long running process, little bit longer, maybe 10 seconds, 5 seconds, 2 seconds. But what this does is basically load balancer, it simply routes. Okay, my request is starts with a simple algorithm for that could be my request start with slash orders, send it to order service. My request start with slash payment, send it to payment service. Same with start with slash user, send it to user service. So it could be as simple as that, right? It's just a router for us. Again, there are ways to handle that as well. You can have multiple load balancer in a you might have heard about master slave model, master slave fashion. Now let's say you have three load balancers. One is master and two are slaves. Now so now when one of the master, let's say, goes down somehow, then other two will do a voting, and they will choose another master. By the time another master is chosen, our, as I said, the cloud providers, they have this capability that they will restart the instance. So they will restart the load balancer for us, and we again have three load balancers based on the configurations and all. We will have another load balancer up and running. So that way you can basically make it 99%. So even very big firms, right, Facebook, Google, they do not say they are 100% available. They say they are 99.99% available, because there is slight chance that when this goes down, it may take 1 second. Even if it is taking 1 second, it is 0.01% chance that your system is not accessible. So this is this is how you can handle the load balancer use case. Next is, okay, when you order, you have ordered something. So, any doubts so far? Anything? Any questions?
Yes, I have a doubt.
Uh-huh.
Can we like set the priority of the load balancer? Like if the master will fail, then the slave will then who will take the
So that's what.
responsibility?
So priority is again it is similar to voting, right? When you are voting, that okay, should I be the next master or should I be the next master, or should someone other node should be a next master? So now you are. This is another way of saying that you one instance has priority over other, right? So this is priority. I understand what you're coming from, but deciding based on priority is another algorithm where you want to decide who is the next master. So voting is another algorithm where you want to decide how the next master should be chosen. So this is totally depends on the designer, right? How you are designing a load balancer and the corresponding cluster. It depends on that. So you can totally have that logic.
Okay, thank you.
Okay. So once you order, right? Once you so we have resolved most of the things. Client sends this, API gateway distributes the load, sends the request to proper service. Load balancer distributes the load. DB's load is distributed. DB is replicated. So we are kind of safe, very, very safe now. Next is notifications. When you send when you order, you get a notification, right? Your food is your order is successful. Your food will be delivered shortly. Then when a restaurant accepts the order, you get a notification that okay, this is the restaurant and they have accepted your order, and then driver is picking your some rider is picking up your order. So all these notifications. So for that, we will have a notification service, of course. Now this is just an abstraction. So basically, the way you send a notification, other systems need not know, right? Why do these systems bother that how you are sending a notification? Your notification could go through SMS. It could go through mobile app notification, push notifications. It could go through email. There are like multiple ways, right? So why? So that's why we have this notification service, which is just a wrapper, and then it basically interacts with third-party services, whether it needs to send it via SMS, via some other form. Uh, but the next question is how you will scale this. So okay, let's add as we discussed, let's add more uh, instances. So we have, let's say, 3 or many instances of notification service. Obviously now we are assuming that there is a load balancer already. Load balancer distributing, notifications are there. But imagine uh, your order service, let's say you have 10,000 customers ordering. So you have 10,000 orders coming in, maybe um, at some rate, right? But notification service will have much more load on it. Why? Because order service will send a notification, then payment, when once payment is done, you want to send a notification. The when rider is going to pick up, there is a service for that, so that sends a notification. Then when your order you get a food being prepared or a notification, right? So the customer, some other service is there which sends a notification. So there are many users of this notification service. So it may, even though 10,000 users are trying to create an order, but you may get maybe a million, or I'm just giving some random numbers, maybe 100k notification request. It may still, even though you distributed, you might have added multiple nodes, it may not be sufficient to handle all the requests. They may start dropping because the servers that you are using, like the Tomcat servers and all, they have a limit. Your system might be at some limit, so you cannot always handle everything, right? So what is the best way? And of course you don't need it a synchronous way, right? What you can do is, yeah, you don't need to wait, right? Client creates an order. Why would you wait for a notification to go to the client and then send a success response? You can simply say, okay, I ordered, I'll send out a notification in a synchronous way, and then immediately return and send client that okay, your is on the screen, you can show okay, your order is there, it's successful. And after maybe a second, you get a notification, okay, your order is successful, we are preparing your order, and something like that. So here comes the use case of queues, message brokers. what you can do is you can simply bring in queue here. So this is the queue. Now what you do is all the services that we have, they will send a message to this queue. Maybe we have multiple other services, they will send messages to this queue. Queue is in itself is a big software in itself. It's a huge software. Now what you are doing is you are simply sending messages to this queue and telling, and then you have in notification service you have listeners to these messages. So at one time they will read just one message. As let's assume that they're reading just one message, so it means that they will be taking it step by step, right? They are not getting bombarded with hundreds and million thousands of requests. They will take their own sweet time to process a request. So even if the notification, let's say sending a notification is a 1 millisecond job, but that one now you're not getting hundreds and thousands of requests, you are getting one request, you process in 1 millisecond, you immediately get the next request. So that way you are making, since you are making this asynchronous, you are not bombarding notification service with lots of lot of load. And queue, again, as I said, queue is again a backend. Think of it as a separate backend software which is again distributed and all that. So whatever we are trying to do here, it we have to be we are assuming that it will be able to handle based on like their Kafka. Examples of queues are Kafka. You might have heard about Amazon SQ, a simple queue service. So these services, they are built and they can handle loads. Kafka handles like millions of requests. So we are assuming that these systems are used across industry. Queue is used across industry and it is able to handle that. So now when the queue message goes to a queue, it evenly distributes the load to all the nodes of notification service, and your notifications are being sent. Your notification service is not heavily loaded. So that's how you have introduced a queue in their design. So now coming back to these slides, coming back to these concepts, microservices. We have created multiple microservices: payment service, order service, then notification service. There could be a user service, registration service. So we have created multiple microservices, and our design is, our backend system is microservices based. Scaling. We have added multiple instances, multiple machines. So now we have horizontally scaled. Obviously, we can always vertically scale. We can keep each machine as 64 GB RAM. Let's say that's the max. Let's say 64 is the max RAM that we can get, which is not true, but let's assume that. So 64 GB, each machine is 64 GB RAM, 1 TB hard disk, and all the best configuration that you can get. So you have vertically scaled, you have horizontally scaled. Availability. We have multiple microservices for each service. We have multiple servers running for each service. So when one instance goes down, you have two other running. So we have made our system highly available. We have same thing we have done with the DB. Same with other services as well. Consistency. Now we have added a wrapper DB or wrapper service around DB, which is making sure that our data is written on all the DBs. Other approach could be again same master slave model, where you have a master DB, you have two slaves DB. When you always write and you always interact with master DB, and the same data is replicated offline, basically asynchronous mode to the remaining DBs. So that is another way to handle this. That way you can always be sure that you are writing to master, you are reading from master, so your data is consistent. DB partitioning we have not done here, but depending on the data that you have that you are storing, you can do vertical or horizontal partitioning. If you have too much data, what you can do is you can divide your order table based on user ID. That okay, user ID from 0 to 10,000 I am storing in X node. then 10,000 to 20,000 I'm storing in Y node. So that way you can do a DB partitioning. And DB replication, of course, that we have done. We even if you have master slave, the master slaves are nothing but your backups, right? A master has all the data, and slaves are the backups. So whenever master goes down, you're sure that your data is not lost. It is there with the slaves. So your data is there. Components wise, we have used API gateway to send the request to appropriate services. Load balancers to distribute the load. Database we have used as of now SQL database. Caching we have not used, but depending on maybe we have let's say a menu service which shows you a menu. So that there we can have we can probably introduce caching in. Let's say you want to show user the hot restaurants in your area. Maybe in Bangalore, I want to show top 10 restaurants. So the logic can be logic for that can be the orders that are getting in for those restaurants. So based on that, I can cache the information of those restaurants and then show it immediately instead of querying DB every time. So that's one small use case of using a cache. But just observe here that we are not storing all the restaurants. We have limited amount of data that we are storing in cache, maybe 10 restaurants, 20 restaurants. We are not storing all the restaurants. Again, this is hot restaurants, so they will change over time. So there will be some logic to remove the restaurants which are not maybe closed or which are not accepting orders. So your restaurants are getting removed from the cache. So we are not unnecessarily keeping data in cache. Message brokers. In the notification part, we have added queues to basically make the notification part asynchronous and easily distribute load on all the nodes. So there we have used queues. Yeah. So this is how we have designed food ordering app at very high level, considering and we have tried to use the concepts and components that we just discussed. Any questions? Okay.
Team, if you have any questions, please
Actually,
feel,
when you say nodes, when you are talking about the dividing the databases on the basis of user ID or whatever, the name or something. So what does this node refer to? I'm not able to understand it.
Nodes, again, sorry, I might have not cleared it. So nodes, instances, machines, they are nothing in like backend systems. They are nothing but like they are same thing. This is so for me this is a node, this is a instance, this is a machine. I can refer. I'm maybe I might have explained. I should have explained this earlier, but I'm referring to the same machine, and maybe these are different terminologies that we usually use. So again,
Actually,
databases.
okay. It means that the collection that we are using, okay, we are dividing the collections or we are dividing the databases on the basis of whatever the user ID or and whatever the basis will be.
So we are dividing the tables. So in a table, you might have orders. Let's say order table. What does order table have? Order ID, user ID. So the for you which user the order was, and maybe some more details about the order, right? Now what we are trying to divide is we are trying to say that okay, for one node or one instance, one machine. Let's keep it common and call it node. So one node will store data for user 0 to 10,000, user ID 0 to 10,000. So when a user with ID 100 is ordering something, we will always store his data in node 1. So we have distributed the data that way. We do not want to keep all the data for all the orders for all the users in a single node in a single table. We are distributing it. We are cutting that data horizontally. Let's say you have 10,000 records, but now when you divide this data, you may have just 1,000 record in each node because based on the user ID
On the same database.
on the same database.
Okay, got it. Thank you.
So yeah, maybe I'll okay. So moving to so this was about this was about the designing a backend application. This is very high level. When you start designing a system, what basic things you need to think about. uh, it was about that, and there's a lot more in that, a lot more to think on when you are designing highly scalable available systems. Yeah, so moving on to the next topic that I had in mind was code quality. So uh, whenever whenever you are coding, right, other people, other your team members may be doing a code review. But code review, I mean, it's not always like feasible to point out every little mistake or every little coding bug that you could have introduced, right? Reviewer is a human, he cannot point out every single thing. So there are like code quality tools which help in that. So first I have some like basic definitions. What is code quality? When your software is free of critical bugs, uh, then your code is said to be that it is of good quality. What are benefits of having a good quality code? um, you might be using a lot of libraries, right, when you're developing applications. So why are you using those libraries? Because you know that they have very less number of bugs. There could be, for doing the same thing, you could have like 5 different libraries in market, but you look for the library which is used by most other people, because you know that that library will not have bugs. So you're reusing the library because it has good quality code. um, when you are writing a good quality code, it's highly visible that okay, when you are adding on top of it, you are adding new features to it, you know that it can easily be enhanced. Hence, in future, when you're developing with a good quality code, it will reduce your time. You don't need to bother about okay, what's happening here. You don't need to go through the code again. It's like very clear. um, Implementing code quality procedures like code review, static analysis, this will reduce your tech debts. So as of now, you might be coding, okay, maybe 6 months down the line, I'll create a ticket and keep it in backlog, and okay, I'll 6 months down the line, I'll take it up and do this. But if you are maintaining your code quality, you are following these procedures, then you will make sure that you don't need to do that thing after 6 months. Yeah, your code is now itself ready, so that you don't need to come at it again and redo things. Because when you redo things, you have to test it again. The QA has to test it again. There's so a lot of bandwidth is going in that. Then there is always chance of regression issues, so you are basically doubling the time that you saved earlier by not following these procedures. Yeah. I have mostly worked with Java and Spring Boot. So mostly in Java, uh, for other languages also there will be a static code analysis tools, but I'm just referring here with respect to Java. So here, what I use and I prefer my team to use is Checkstyle and Findbugs. Uh, Checkstyle basically it helps you have a standard in the code. So, for example, one of the very easiest thing is basically when you add brackets, you have to leave spaces in the front and the back. Why? Because that makes your code readable. If you don't have many spaces, right, your code will be too compact, and like it will be not like you will not, other developers might have problem reading it. So these are some Checkstyle issues. Checkstyle basically forces you to follow a standard, so that it's your code is more readable. It forces you to have naming conventions, at least in Java. So there are like certain conventions that are followed across industry. So it has rules to check that on your code. It improves your code readability. Find bugs finds a little bit deeper issues in your code, which might have been missed by your reviewer or yourself. uh, it may find that okay, something is going to be always null. So at some point you may be getting null pointer exception. You might have missed this, but when you are deploying your code, then you will basically face this. Then you have a bug, you have to fix that, and then the whole cycle begins again. So you by using these tools, we can possibly get these errors beforehand, fix those, and at the time we will have less these kind of annoying bugs. We'll have more functional bugs, so which are okay. So you may find like whatever language you guys are using, you may find static code analysis tools for you for those as well. Yeah, so that's all I had. Any questions?
Pratik, I have a question regarding the last part, like static code analysis, right?
Hmm.
I mean, not a very technically sound person here, just, but what I understand from that is I am saying that this code is, that this code is, this is what is the output, okay, for this code, and it is not changing, right? So every time if I am suppose working around that, so like I am just using that maybe check style or finbug, right, to just ensure that the code is untouched. Like what exactly, like if you want to explain a PM in that term so that I can also help use it. I can
Hmm.
ask, I can implement this also for me. So what do you like? Explain me a little bit in that way so that I can implement such things.
Okay, okay. So
Yeah.
Chextile, as I said, Chextile basically forces the developers to follow a standard. There are
Mm-hmm.
standard rules. So when a developer, as I said, it improves your code readability. So it will not basically when other developers are reading your code, it's easy to understand for them to read your code. So that
Mm-hmm.
makes so when let's say one of the developer is not available, he's on leave or he left the company, others can
Mm-hmm.
easily come. Okay, this code is readable, it's easy to maintain, they can easily understand what the code is doing. So Checkstyle forces those kind of standards. Find
Mm-hmm.
bugs basically it tries to find some minor small bugs that you have missed. For example, one example was null pointer. So you might have initialized a variable with null, but down the line you are using that, but you're not uh, initialized it with some actual value. So when you are deploying your code, when you are running your code, you will definitely get a null pointer, right? It may be possible that the developer missed it. It's something quick was needed, some urgent production issue. So when the reviewer missed it, it was deployed. Now at runtime you are going to face that. So find bugs, find those kind of issues. It is not so, and these codes, these analysis tools can be incorporated in like your build process. When you are building your code, you can
Yeah.
incorporate this. So every time a developer codes on something new, he can basically when he build this his code, he can see if there are any bugs that
Mm-hmm.
the tools
Right
has
at
found.
the beginning, right at the beginning, of, if we're using such tools, that will help us to overall have like automatically this tool is basically forcing me to follow the standards in a simple
Correct,
way. Correct?
correct.
Interesting. Interesting. Nice. Yes. So please, guys, do you have any questions? Team, any questions? Everything is clear. Everyone then has to implement all of this, and I should see this. I'm personally going to come to everyone and I'm going to check, are we following this or not? Divyansh?
Yes, Varun.
Yeah, I'm going to check if you're using this check style or any other tool that we will be using. So you only are going to tell me now which tool should we use and how are we going to implement. That's fine with you.
Hello.
Anyways, so yeah, you're audible.
Okay.
All
Okay.
right. So I think team
Yes.
doesn't have any question. It means that Prateek, honestly, I loved the session. So first of all, thank you so much to take time out of your busy schedule and host this session. So thank you so very much.
You're welcome.
The entire, this is from the entire team, and even I was able to understand. As a project manager, these things are technical for me, but I was able to understand. So you have broken them down into such a simple way. I know that you were like quite nervous. So see, that's what I told you. So please, we would love to have you again and have such sessions. It was really very insightful. And yes, it also gives me as a, in spite of not being actually in programming and all that, I was able to understand, okay, this is how the system works. A very interesting topic. I might personally reach out to you because now this has gone, like, the curiosity level has gone up now. So yes, thank you so much for that. And yes, Vaibhav, thank you for contacting Prateek and having this entire session, for us, so that we improve, we learn, and we grow together. So
Yeah,
team, this is there why we stop and pause our work, because whenever we are working, Pratik, I'm sure even you will agree to this, that in 10 years of work, you are not, what you started back then in 2012, correct?
yeah,
So lot of things you have grown, and if you are sharing your experience to these guys, I'm sure there's a lot more to learn. It cannot be covered in 1 hour session. So I'm obviously going to reach out to you for more such sessions.
sure.
So yes, and team, this is the time where we learn from the expert, okay, and grow, learn. What happens is, if we are in loop of work, right? We have deadlines in our hand, we have projects to
Correct.
jump on, we forget to learn, which is super important. Even no matter what is the position, when have you started, it's important for us to keep on the learning graph high, right? So I'm sure Vapor will also agree with this, and that is the main reason he wanted to, have such sessions, so that we as a team can always learn, and have the knowledge what we have is to be always expandable. So yeah, thank you so much, Vapor. Thank you so much, Prateek. And yeah, anything else do we have, Vapor? Vapor, you are on mute if you're saying something.
Yes, yes, yes. So yeah, I'm here. Yeah,
Okay. Oh,
yeah.
yeah.
So thank you so much, Pratik, for taking out the time. I believe it has been a valuable session, and we will definitely reach out to you for any follow-up questions.
Sure, sure. So,
Okay.
uh,
Yep. So wrapping it. Uh, thank
Okay.
you, everyone.
Thank you, everyone.
Thank
Thank
you.
you, Pratik. Yeah. Thank you.
thank you,
Bye.
guys.
Take care.
Bye
Bye.
bye. Yeah.
Thank you, Pratik sir. Thank
Thank
you
you,
for
Pratik
thank
sir.
you, sir. Bye, bye.
Bye.